Okay, hi everyone. So I'm starting the talk this afternoon. First, a few announcements. So there will be a discussion after this talk and the coffee break, but that will be just free discussion. You are free to be anywhere. And then, but there will be a discussion session from 1:30 to 3. 1:30 to 3:30 tomorrow, and also on Friday, 1:30 to 3:30 tomorrow. Then we will actually be here for a more formal discussion. But the discussion from 4 to 5 will always be free discussions. For my talk, I like to talk about Hawking radiation after the scrambling time. So I would like to first review some basics about Hawking radiation. That's the first part of the talk. And then in the second part of the talk, I will talk about my works with my collaborators in which we found UV models that produce quite different Hawking radiation than the standard story. For the references, we have a review paper. And also, I'll talk about the breakdown of effective theory. And then 3 different UV models, the generalized uncertainty principle, and also a string field theory model, string field theory motivated model, and the commutative geometry model. So let me first review some basic stuff so that you know exactly what context I'll be talking about these modifications. So basically, Hawking's, or the information paradox is that Hawking did a calculation in effective field theory. And the conclusion is essentially incompatible with string theory and our understanding of quantum mechanics, as Samir was talking about this morning. So a big question is, where did Hawking make a mistake? And many people checked. Many people didn't believe his calculation in the beginning, but checked carefully and finally agreed that he didn't make a mistake in effective field theory. But it's possible that effective field theory actually is not reliable for the prediction of Hawking radiation. So firstly, of course, you can imagine that string theory or some UV theory would cure the problem. But the first question is how effective field theory breaks down. Because if it doesn't break down, if there is no Lorentz invariant Transplanckian physical quantity involved, then effective theory has to be right? We can use effective theory like standard model in curved background, like what we do when we predict results in collider physics. So we can describe the burning of a piece of coal or the evaporation of water without seeing any information loss if we use effective theory. So unless effective theory breaks down, you cannot say that there is some string theory degree of freedom that's not taken into account, and therefore you have problem with information. That's not a reasonable logic. So the first point, the first part of the talk, I'll try to review and also explain how effective theory breaks down. So there will be a calculation with the Lorentz invariant quantity that becomes Transplanckian. And then the second part of the talk would be how or what kind of UV physics help. Because even if effective field theory breaks down, many people have tried all sorts of different UV models, but still find essentially the same prediction of Hawking radiation. So the question is how you can imagine any sensible UV physics that would give you a dramatically different prediction than Hawking's. I want to emphasize that in this talk, I'll only be talking about dynamic black holes, meaning that I'm not going to talk about eternal black holes. So I'm going to imagine a large body of low density dust collapsing under gravitational force and then form a black hole. And so the whole thing is a dynamical process. It's time-dependent process. In this way, we can specify the initial state in a well-defined way. We just say that in the beginning, we have the Minkowski vacuum. When the density of the dust is still very low for the radiation field, we can assume that the radiation field is in the Minkowski vacuum. So we know precisely what quantum state it is. And then we can just use standard quantum field theory to predict what's going to happen afterwards. Please feel free to ask questions at any time. So I'm going to use A to denote Schwarzschild radius. I'm only going to talk about Schwarzschild black holes with spherical symmetry. And I'm assuming that it's much, much larger than the Planck length. Also, I'm not going to distinguish Planck length with string length. So there's a UV length scale, which I'll write LP or LS. I'm going to set velocity of light to be 1, Planck constant to be 1, and so on. But I'm going to keep Newton constant, which is Planck length squared. Okay, so in the so-called traditional model, the model that people believe in following Hawking's calculation, we typically assume that the density is very low, like what Samir was saying, and there is no drama around the horizon. So we assume that the initial state does not involve igniting a nuclear bomb around the horizon. So we have a very mild initial state, and with equivalence principle, every observer in the free fall feels like the same as floating in space. So if the initial state is vacuum, they feel like they would stay in vacuum for a long time. And also, since we're considering a very large black hole, so the curvature is of order 1 over a squared is also very small number. So you can take a sufficiently large black hole so that the curvature around the horizon is actually smaller than the curvature on Earth, for example. And we know that effective field theory works very well in such a small curvature background. So I'll first try to reproduce Hawking's result, but to do that, let me start with the Schwarzschild metric. So it's the same expression Samir wrote earlier, and we can also do change of coordinate system. We define the Eddington retarded time and advanced time, where R star is the tortoise coordinate. And then this metric is equivalent to this metric. Hawking radiation starts when the collapsing matter is close to the horizon. So if we write down the Penrose diagram, this is the horizon, and we have collapsing matter falling into the horizon. So for a distant observer over here, the observer is going to start seeing Hawking radiation when the collapsing matter is at a position close to the horizon, right? So if I use capital R to represent the radial coordinate for the collapsing matter, then when this is when R minus A is much smaller than A, along the light cone, people are going to detect Hawking particles. When the collapsing matter is still here, you would not see any particle over here, right? So this is in any way a time-dependent process. So since Hawking radiation is relevant only when we are close enough to the horizon, we can approximate the metric by expressions valid around the metric. Sorry. So we use cross-coordinates. We have the retarded and advanced light cone coordinates. But in the near horizon region, when R minus A is much smaller than A, I'm always talking about only the space outside the horizon, because as you can see from this diagram, the Hawking particles we detect over here only involves the geometry outside the horizon. So what happens inside the horizon is irrelevant to us by causality. So I always assume R minus A is larger than A. And then with this approximation, we can rewrite this in terms of little u over here. The light cone coordinate suitable for distant observers. For distant observers, when R is much larger than A, this term is much bigger than the rest. So R star is essentially R. So this is the usual Minkowski light cone coordinates for distant observers. For observers in free fall, the cross-co light cone coordinates is more suitable. And these two light cone coordinates for near horizon, freely falling people and distant observers, they are related roughly by this exponential relation, and this is the origin of Hawking radiation. Similarly, we can approximate the advanced light cone coordinate by this exponential relation. And the near horizon region we talk about is for cross-co U to be less than 0, and its absolute value much smaller than Schwarzschild radius A. And in terms of these coordinates, the metric is approximately this. So if you look at the first part, it's essentially the same as a flat Minkowski space. But it's not flat because this radial coordinate R is a function of U and V. And outside the collapsing matter, it's approximately this. Inside the collapsing matter, it should be like that. So for simplicity, we are going to consider collapsing matter at the speed of light. So the trajectory is like this. And also we are considering a thin shell. so that when you solve the semi-classical Einstein equation or the wave equation of the radiation field, you can just use boundary condition to match the solution outside and inside. So this is the typically thing people do to simplify the derivation of Hawking radiation. So in the near horizon region, basically you can use this metric, and the only difference between inside and outside is how the radial coordinate depends on U and V. U and V are valid light cone coordinates, both inside and outside the collapsing matter. Any question? So because of this relation, the light cone coordinate capital U and little u, they have this exponential relation, which is the reason for Hawking radiation, because at large distances, observers define particles by positive frequency waves, and the frequency is defined in terms of little u for massless fields. But for freely falling observers around the horizon, they define particles by positive frequency modes defined with respect to capital U. But these two are not the same, and this exponential relation is saying that what you call a particle here is different from what you would call a particle for freely falling observers. And the difference tells you that for freely falling observers, they would say they are in vacuum, but the same state, assuming that the state propagates out without much change, assume weak interactions with the background, then the same state over here would be identified by distant observers as a state with Hawking particles, as an excited state. So that's the origin of Hawking radiation. And so basically Hawking radiation is just a reinterpretation of the vacuum state. So we have an initial state, which is the Minkowski vacuum of the infinite past. And this vacuum state is reinterpreted as Hawking radiation. From this statement, you can see why Hawking radiation doesn't carry much information, because it's the same for any collapsing. As long as you have something collapsing, you basically always have this relation, and you always have this reinterpretation, the same interpretation. So this radiation doesn't carry much information, and therefore this is the only source of information loss. If all the radiation arises from such a reinterpretation, then you would have information loss. If you have other ways of decaying or radiation, like usual radiation, like burning a piece of coal, then it's fine. That radiation doesn't cause any information loss. So I'm going to focus on this definition of Hawking radiation, just the reinterpretation of the Minkowski vacuum in the infinite past. All other radiation that there could be are not my focus, as they do not lead to information loss. And to derive this Hawking radiation, what we do is we look at the wave equation in the Schwarzschild background. So in the Schwarzschild background, we have, in 4D Schwarzschild background, you have a Laplace equation for massless fields. And then typically for simplicity, we consider the S wave reduction. So we consider spherically symmetric waves, meaning this 4D field is now expressed like this in these onsets where the phi, this phi is a 2D scalar satisfying a similar relation. This part is the 2D wave equation for massless field in 2D. This part is the correction due to Schwarzschild metric. But this part is actually small. I mean, in the near horizon region where R is around A, this term is nearly 0. At very large R, when R is much larger than A, this term is very small. So the contribution of this term gives you a modification of the gray body factor, but it's typical to ignore them for order of magnitude estimate of Hawking radiation. And only when you ignore them, you get the thermal Planck distribution. Otherwise, you get the gray body factor. So we are going to ignore this part. And we approximate the wave equation by this equation. And then the solution is easy. For outgoing modes, the equation is this, which means that phi is a function of u only for outgoing modes. For Hawking radiation, we only care about the outgoing modes. And since little u and capital U are functions of each other, so you can also say this is an arbitrary function of capital U. So to derive Hawking radiation, we expand massless scalar field, the 2D scalar field, in terms of little u and capital U. But they are the same thing, right? This can be expressed as a Fourier expansion with respect to capital U or as a Fourier expansion in terms of little u. The suitable normalization. So when you quantize this field, the coefficients are creation annihilation operators defined with respect to the vacuum in which positive frequency modes are particles. So if you use capital U, so for freely falling observers, their time coordinate would say positive frequencies are associated with positive capital omega. And they would say this is the creation operator, this is the annihilation operator. For distant observers, they would say little u is their time coordinate. So positive frequency modes are those with positive little omega. Forgot to say that these are positive. And so this is creation operator and this is annihilation operator. Sorry, I wrote it the opposite way. Sorry. Well, I mean, you can define it anyway, but to be consistent with my paper, we define it this way. So we were saying that initial state is a Minkowski vacuum in the far past. So for them, the suitable time coordinate is capital U. So the vacuum here, the Minkowski vacuum, before the matter collapses, is defined by being annihilated by the annihilation operator A, not B. On the other hand, B and A, they are related to each other by the Bogoliubov transformation. So you see, although this vacuum state is annihilated by this state, it's not annihilated by this annihilation operator because it involves creation operator. And therefore, when a distant observer is trying to detect how many particles are there in this Minkowski vacuum, when they use their detectors created with respect to their time coordinate, the number operator is defined by this creation annihilation operator B, and then this is non-zero. So this is Hawking radiation. So we assume that this vacuum propagates out without much interaction with the background to large distances where people define particles using the creation annihilation operator B. And since these two expressions are expressions of the same object, you can find from the relation between capital U and little u over here, the relation between A and B. So these Bogoliubov transformation coefficients, they are fixed by this exponential relation. But in principle, if you have any two coordinates, U and U, depending on the functional relation, you can find Bogoliubov transformation coefficients. But when you have this exponential relation, this characterizing parameter little a would tell you that you get a thermal spectrum for this number operator at large distances. So to find alpha and beta, basically you just do Fourier transform of either one, right? So in principle, we can all do that and check that this is a thermal spectrum described by Planck distribution. But we like to do this more carefully because given a frequency little omega or capital omega, they are constant frequency modes, so they spread over the whole space-time. But physically, we have observers at large distances detecting Hawking particles one by one. So we should look at wave packets. So every time they use an en route DeWitt detector to detect Hawking particle, the detector specifies a particular wave function for the Hawking particle. So let's define a generic wave packet for a massless outgoing particle. So this function, little f, is a function centered around omega 0. If this is real function like a Gaussian, then U0, this constant U0 would be telling you where the center of this wave packet is. So given this F, you get psi. It has a wave packet. And the frequency would be centered around omega 0 with a spreading of scale delta omega. For this wave packet to be relevant to Hawking radiation, we assume that omega 0 is of order 1 over A because the Hawking temperature is of order 1 over A. Also, we assume that this is much smaller than omega 0 or 1 over A because only this way we can, by detection, tell what is the spectrum of Hawking particles. We want to reproduce, by detection, we want to compare the result of measurement with thermal distribution. So given a wave packet, you can define the creation annihilation operators corresponding to this wave packet, right? So B psi is the inner product of psi with the quantum field. And then you can check that when little f is suitably normalized, if the norm of f squared is 1, integrates to 1, then the commutator of these two is 1. So they are creation annihilation operators for this wave packet. And then you are measuring the number, expectation value of the number operator B psi dagger, B psi dagger B psi. Yeah. So we want to compute this thing. Since this coordinate little u is only defined over here, it's always outside the horizon. So the wave function has a support only outside the horizon. So this number operator only depends on the geometry outside the horizon, and the result would also only depend on what's happening outside the horizon. So we don't care about whether there is really a horizon. So this is a little bit different from later derivation you may see in review papers. In review papers, often they consider the whole Schwarzschild space-time. They divide a wave function, they divide the field into the part inside and outside the horizon. But in that calculation, you don't really see how the radiation depends on time. As we were saying, when the collapsing matter is still far away from the horizon, there is no Hawking radiation. So that kind of calculation can never tell you that, but that is something we expect. So if we care about the time dependence of Hawking radiation, we have to consider such wave packet. And this is actually how Hawking initially did in the paper. Yes?
So in this language of the psi function which you define, is it really tricky to make a complete orthogonal basis of such modes inside?
Yeah, I don't need the complete basis. I have en-route DeWitt detectors, so I'm just wondering about what.
Just one detector.
Yeah, what you detect, whether there will be particles at a certain time U0.
So you can't get the temperature from this kind of calculation, can you?
We will actually still get an approximate temperature. Yeah, so that's why we need delta omega to be much less than omega 0.
Okay.
So with such assumptions, actually, we still get the temperature.
Okay.
So I'm going to show this calculation. So firstly, because B sub psi is essentially just a linear combination of B sub omega over the little f. So you expect that this is giving you something like this. So you have these factors because when you plug in B dagger B, then A dagger gives you non-trivial result over operating on this vacuum state. So you get beta star beta, like this. And then you know what they are. So you just plug them in, and then you get some factors from the expression of beta. And then you have the omega dependent part, capital omega dependent part, which looks like this. So this part is what's coming from beta star beta that are independent of omega. So this part gives you the Planck distribution. And this part we can carry out a change of variable. Let's call capital omega 1 over 2a exponential minus I guess it's plus u over 2a. You plug it in, you get little u integration over little u from minus infinity to infinity, exponential minus I omega minus omega prime u. So this exponential minus I omega u multiplied by f0 integrated over omega is essentially the wave packet, wave function. And then you also have the conjugate of that from integration over omega prime. And so you see that apart from this Planck distribution factor, what you have is just a normalization condition for the wave packet. Essentially like that. In this calculation, we have made some approximation because of this condition. I should say this is omega 0. That condition says that little f is a narrow function. So when it's multiplied by something that depends on omega, but if this part has a variation over omega of scale 1 over a, this is much narrower than that. So you can simply replace the omega in here by omega 0 and pull it out. So that's how this condition allows you to still get the Planck distribution factor approximately. And then this is just normalization condition. So this is how you get the result. Actually, if you do this calculation, this would be infinite. This would diverge because you are having two identical frequency, the operators at the exactly same frequency multiply. So this is the physical answer. And there's one thing to note here, that is, if I had a cutoff in the frequency, suppose I imagine a regularized, UV regularized theory in which the frequency for freely falling observer has a Planck scale cutoff. capital omega cannot be larger than capital lambda, then I replace this by capital lambda. And then this change of variable would change the upper bound of little u to 2a log 2a capital lambda. So this upper bound is changed to 2a log 2a capital lambda. So it's saying that if you are detecting Hawking particles beyond a certain value of u, you would not see anything if there is a UV cutoff. The Hawking radiation would be simply cut off beyond a certain time. Of course, this is not a very good model because this is saying that we have no oscillation modes within at the frequency omega 0 over here. So it would mean that if now there is a vacuum coming from a near horizon region passing us, suddenly we cannot create certain oscillation modes. So this is not really a physically sensible theory. It's just like if in inflation, Transplanckian scale modes are later infrared modes, but you have to say they are still there, right? So you cannot say they are not there. So this is only a way of saying how there could be a time dependence if you modify UV physics. So if I don't use a cutoff, which is weird, but if I have other UV physics beyond a certain UV scale, I could, in principle, modify Hawking radiation. Is there any question?
But that wouldn't change the temperature, just gray body factor.
It's just an amplitude.
Yeah.
Yeah, that's right. So the Hawking temperature would remain the same, 4 pi a under 1. Yeah, that's right. So that part is actually only determined by coefficients in beta. And because we assume delta omega is small, that factor just comes out. So it's always there. So in all the calculations below, in every UV model, we are not going to change the Hawking temperature. Hawking temperature is indeed robust. So there are hundreds and hundreds of papers claiming Hawking radiation is robust, but 95% of them are talking about Hawking temperature. And that is indeed robust. So we cannot change that. That is too robust. Sorry?
In the presence of a cutoff, wouldn't you have to account for subleading corrections and what are their effects?
Right. So if there is really a cutoff, then you would see no Hawking radiation after a certain time.
Okay, so but you're saying like if you add any subleading corrections coming from this, it doesn't change that, if that result.
It would change it. So I'll give you 3 examples later to see how it may be changed. Yeah. Yes.
Can you use this formulation to study correlation of the Hawking quanta?
Correlation of
The
the...
Hawking quanta produced at different time. Can you,
Ah.
you have a wave function and you have a language. But
Yeah, so in principle, you can do that.
you have to
We haven't
use,
done that.
Interaction.
Right. In principle, you can do that. So basically, this is only a review. This is the same calculation, essentially the same calculation Hawking did.
I have a question.
Yes.
Okay. Do we have any way or possible way to detect this NW, N omega?
And
For example-
this one?
Yeah. For example, could we detect it from the superradiance region and for rotating black holes? And do we have any direct evidence to that the observable, depending on observable, is still possible to detect?
Yeah, I think this is not physical because it involves detecting something all over the whole space-time. So the physical one is this one. So this one you can detect using an Unruh-Dewey detector
Yeah,
at
but
a certain
en
time.
route way is possibly just air nog, I think.
Huh?
En route temperature is just air nog way,
Uh-huh.
but it's not direct. I say, could we have any evidence from the more direct in the context of the curved space-time QFT?
Not sure I understand the question.
I mean, could we have some more direct test or evidence to the observable can depend on how we observe it?
Oh,
Not theoretically.
well, this is standard quantum mechanics. I don't know.
I mean,
I think that's verified. Huh?
Yeah, you use the theoretic one to say that, but do we have any direct evidence from the experiment to know that?
I mean, in principle, yes, right? I mean, you just construct en route detector. You have a atom with a certain Hamiltonian, and the interaction Hamiltonian couples the field with some operator acting on the atom, and then you calculate the transition amplitude, and that transition amplitude would be related to this number operator expectation value. So this is physical. You can actually measure it in experiments. So that's review, and now I'd like to talk about our work in which we showed in one way the breakdown of effective theory. So this work was done with Yuki and Kawai-san. So basically, usually people want to say there is a Transplanckian problem because we have this exponential UV. We had this du dv, du equal to u over minus u over 2a. So the frequency capital omega defined with respect to capital U, and the frequency little omega defined with respect to little u would be related by the same exponential factor, roughly speaking. Of course, actually, if you have a single frequency little omega, actually you cannot define capital omega. So this is like the central frequency relation. On the other hand, such a quantity, the frequency defined with respect to light cone coordinate is not a Lorentz invariant. So even though you have this exponential factor and the exponential factor gets exponentially large at large little u, and you get a very large capital omega, it doesn't really mean effective theory breaks down because it's not Lorentz invariant. But there is, in fact, a Lorentz invariant quantity, which is the center of mass energy squared for the collapsing matter and Hawking particle. So as a scattering process, you have particles collapsing. And every collapsing particle has to have a momentum, ingoing momentum, which is at least of order 1 over a, because otherwise its wavelength is too long to fit inside the black hole. So so PV prime has a minimum value of order 1 over a. And then you have outgoing Hawking particles, which have momentum given by this frequency. So its order of magnitude is omega times this exponential factor, and omega for Hawking radiation has the order of magnitude of 1 over a. So this center of mass energy squared has a order of magnitude that grows exponentially with little u. So when little u is larger than what we define as the scrambling time, well, this is following the definition of Sakina and Susskind. when u is larger than this quantity, you see that its exponential is larger than a squared over Planck length squared. So this is then larger than.
You what we call do not set of the wave factor.
U0, yeah, that's right, that's right, that's right. Thank you. This is actually U0. Sorry, I'm being sloppy. But also, this doesn't really say this would actually do anything because when the collapsing matter is entering the horizon, there was no particle for the Hawking particle yet. It was still just vacuum. So we have to define a physical quantity that we can detect, in principle, whether something actually happens beyond the scrambling time. So our consideration is to, yes?
So could you sketch where these particles are on a Penrose diagram? Because the one thing I'm worried about is, as you were saying, at the time this stuff is falling in, it's passing through vacuum. And the Hawking quanta that you're wanting to have some large transplanckian effects with doesn't really appear until sometime later.
That's right. So that's not yet a reliable argument. So I'm going to give you a more reliable thing. That's right. That's exactly, yeah. So this cannot be taken seriously as a signal saying that effective theory breaks down. But we can do the following. We consider in any quantum field theory, in principle, you have many non-renormalizable interaction terms that you ignore because you assume your physics happens at cis-Planckians, below Planckian energy scale. So a signal of breaking down of effective theory can be found if the contribution of non-renormalizable terms becomes dominating for certain physical measurements. So what we're doing is going to consider the transition. So originally, Hawking radiation is about Minkowski vacuum in the far past propagating to approximate Minkowski vacuum at large distances. Now we ask whether you would get a large transition to excited states. So a state with two more Hawking particles on top of the usual Hawking spectrum because of interactions due to non-renormalizable terms. If this transition amplitude becomes large, it would mean that effective theory is not reliable, right? So I can take this as a signal. So what we want to calculate is this. So let's call this, so I have two wave packets. Sorry, so it's not omega 1, omega 2, it's psi 1, psi 2. So I have en route DeWitt detector for wave functions psi 1 and psi 2. And then I'm asking whether this is large. And I'm considering non-renormalizable interactions. So as examples, we considered these two possibilities. Sorry, this is 4D field. So for n larger than 0, this interaction is suppressed by Planck mass. So usually we say we can ignore them. But if the contribution of this term gets large, it would mean that there is something trans-Planckian, physically trans-Planckian, right? So we just calculate this quantity instead of relying on that argument. Yes. Compared to Hawking radiation. Hawking radiation. Compared to, so if I get a flux from this term much larger than Hawking radiation, the flux of Hawking radiation, then this is large.
It would mean back reaction. We need to think about back reaction to the effective field. What would that mean?
Yeah, so it actually doesn't mean anything particularly except that it's the breakdown of effective theory. Because what I'm going to show later is that for larger n, the contribution is larger. And in the effective theory, in principle, you have all the terms with arbitrary large n. So there's no convergence of the theory. So it simply means that you cannot trust effective theory at all.
It's not a good way to do calculation using.
That's right, that's right.
Even though they're suppressed by powers of the Planck mass, it doesn't matter because the series itself is very large.
That's right, that's right.
Hello. Why don't you consider this an intention? And the other question is, n is a fixed number here?
And for every term, it's a fixed number, yeah. But in my calculation, we can leave it as an arbitrary integer.
You say arbitrary integer to just sum over the n integer, or?
We cannot sum because it doesn't converge.
Oh, okay. So why do you consider this potential or this intention term?
This is one of the infinitely many interactions. So I'm writing this down first, but you can keep going. So another one is to have these replaced by, say, terms in, say, psi is, maybe I shouldn't use psi. What should I?
So if you consider such infinite terms, does it mean that you can see the UV compression?
I cannot. I'm only trying to argue that effective theory breaks down.
So what is beta sin compared to the 5-4 term?
Yes, people have considered 5-4 before us, long time ago.
Yeah.
So actually, in the 1980s, when people still, I think at that time, not everyone understands the notion of effective field theory, that you should actually consider non-renormalizable terms. There was a time when people don't consider, I don't know, that was my impression reading papers. I wasn't doing research at that time, so I'm not totally sure. But anyway, so at that time, people did consider 5-4 and other renormalizable terms in Hawking radiation. And actually, in a paper, they explicitly said that these corrections are small, but when there are more derivatives, the effect is larger, even though it's still small. So we just look at many derivatives.
Yeah. So if we can put the many derivatives, I just expect that is maybe a better point is that you have an infinite conductor, then it can make it as the UV finite, but you said it's not here.
Yeah, so after this, I'm going to consider 3 UV models in which I imagine you can resum all the infinite many terms and then calculate Hawking radiation there.
So in this model, you can do that.
In this model, we don't even know what is lambda n, so there's no way of doing anything like that. So this is a generic.
So you say later. And then you will say later what is UV copy, you can do the summation.
Yeah, I'm taking it step by step. So at this step, I'm only showing the breakdown of EFT.
Okay, thank you.
So yes, thank you. So later on, it would make sense to consider different resummation of the infinite derivative terms.
So you're pointing that you, as a state. And as a generic set of these non-renormalizable terms, you're considering this form of.
You can consider any form as long as there are many
But
derivatives.
is this like the simplest example, or is this like the most computable example that you know of? I'm just
This is the most computable, I think. Yeah, easiest to compute. I don't know. Maybe there are ones easier to compute, but this is already easy enough. So you can replace this part by, say, collapsing matter field psi here, or but I keep it quadratic in the radiation field so that it's easier to compute. Yeah. So you just plug it in here, and then you can expand this field in terms of either creation annihilation operators little a dagger, or little b dagger, and you plug it in here, and you know what this is, so you just compute. So in this computation, we all know how to operate, how to derive the result. And then you will see that there is a exponential factor. So actually, you will see that there is this factor appearing with a certain power in this expression. And therefore, effective theory has to break down. So you can find the explicit calculation in our paper, but here because of limit of time, I'm only going to show power counting. So firstly, the Ricci curvature. We have the Ricci curvature due to collapsing matter. So you have collapsing matter, and then this is of order 1/a squared. But this is non-zero only for the trajectory of the collapsing matter. In other empty spaces, this is 0. And then you have the covariant derivative. So when you take RVV over here you would take covariant derivative with respect to capital U. This contraction has the largest contribution. And this one would, of course, give you that capital omega. And this is of order 1/a. So you can see that the contraction of the indices does give you that center of mass energy squared. And then you also have a normalization of field operator that gives you 1/a, because this was defined to be this. And also you have contribution from the measure, and also the wave packet. The wave packet in terms of capital U is exponentially narrow. So this is a small number. This is like a to the 4th. So because of this exponentially decaying factor, if you don't consider higher derivative interactions, you don't get a large contribution. But you need sufficiently large powers of derivatives so that you get a sufficiently large power for exponential U to counter, to cancel this exponentially decay factor in order to get a exponentially growing result. So plugging all of these so we have lambda n, and we have a suppression by Planck mass, and we have the measure, and we have n factors of Ricci scalar, Ricci tensor. And then we have the covariant derivative. And then normalization of the field. So these give you a squared to the power 2n. And this is our center of mass energy squared. And because of this, n has to be at least equal to 1. So anyway, this is in the end so U0, so this is exponentially large after the scrambling time, as long as n is larger than equal to 1. The same definition we had earlier over there tells you that this is larger than 1, so a positive power makes it larger. And after U0 gets bigger and bigger, this exponential is larger and larger, and it's larger with larger n. So it tells you, yes.
Intended to be an interaction between the infalling matter and the outgoing radiation?
Yes.
So, but they're displaced along the horizon. So
Displaced along the horizon. So in the, I'm not sure what you mean. I mean, we have everything well defined, right? We just do an algebraic calculation.
right. I'm confused that the picture I had was, okay, I have some shell of ingoing matter, okay, and then I'm Hawking particles that are being created somewhat further along in some, affine coordinate along the horizon.
That's right.
So if my interaction is a local interaction, in what sense is it operating if, my
that's
infalling
right.
radiation is
Exactly.
here, my outgoing radiation only gets produced over here. So in what
Exactly.
sense is
So
this
that's why we didn't stop at that line, because intuitively it's hard to say that we do get something large. But this part of the calculation is purely algebraic.
But you wrote down a local operator.
This one, yeah, it's a local operator.
Okay. So how is it having an interaction between or is this just something that is purely some effect of some correction to the Minkowski vacuum?
Yeah, it's a correction. That's right. I mean, you
Okay, so
have
then
two more particles on top of.
Okay. So it's some it's like some vacuum instability. It's not, in other words, my question is maybe in part, if it's not an interaction between the infalling matter and the outgoing radiation, it sounds more like it's some kind of large correction to the vacuum state near the horizon rather than some process by which the infalling matter is transferring some information to the outgoing.
Yes, you can say that.
Okay.
Yes, thank you. Yes.
So I guess I'm just asking the usual naive question about the critical coordinates. If I just went to some smooth local coordinates, and maybe not the u and the v, but just some smooth coordinates, and the Ricci r mu nu is just something very gentle. It's on the scale of the, I could take a star where it's not sharp or anything.
You mean calculating this in a different coordinate system, or?
Yeah, just calculate.
Yeah, we actually did both calculation twice, once in Cresco, once in the little u and v.
Okay.
Same result. So the difference is just that when you use Cresco coordinates, this is large, while GUV is 1 or 1/2. And when you use little u, this is small, but then this is large around the horizon. So either one becomes large. So as long as it's a Lorentz invariant quantity, so it doesn't really matter which coordinate you choose. So we actually did both to make sure.
So maybe I'll just follow up with a couple of, I'm still trying to fiddle around with that equation. If I take the derivatives and integrate them by parts so that they actually land on the R, I could do that, right?
Yes.
The grad mu I could integrate by parts, so it becomes a derivative on the R.
Yeah, we have a lot of terms that turns out to be not dominating, right?
So if the grad mu was generating the positive powers of e to the u over 2a, if I integrate them by parts and put them on the R.
Sorry, sorry, which part?
He's saying take grad mu1 to grad mu1 and phi and do n partial integration. Yes?
Yeah, so just put all the gradients on the Ricci tensors so that there are no derivative left on the phi. Can I see that I will still get the big terms e to the u0 by 2a in that language?
Well, I mean, if you move this by integration by parts, you would get both acting on this and that, right? You would still have more derivative on this thing.
The other guy.
Yeah. The total, I mean, my counting doesn't really matter
So
which.
Okay, I think I understand. But maybe then one last question. If you want to compute the S int, which is a number, and the phi is an operator on the right side, still looking at that equation in the bottom right corner of your board, then do you want to sandwich that in some state? First, I mean, you want to have the vacuum. Is the phi a field there, or is it a number, the phi?
Phi is a field. You are talking about this phi?
Yeah, that's
that's a quantum field of radiation.
He's calculating the matrix element of S in with the Minkowski vacuum and two more particles.
yeah.
M, whatever you're calling M, right? That's the invariant one.
Right. That's right.
Right. So in that last equation down at the bottom right board, there should be a vacuum on the right and two B's on the left.
Yeah, that's right. That's right.
This one.
And this is that.
So
That's
I
right.
guess what I'm looking for here is the same thing that Emil may have been asking about. Where in this is the information that if I follow the particle back, it has a T mu near infinity because it's a real particle. And as I come backwards, if I compute its T mu, it's actually zero.
Uh-huh.
The reason the T mu vanishes is because of the vacuum fluctuation somehow cancel the T mu of the
Yeah,
mole
yeah,
and so on.
yeah. We are not saying there is a firewall or anything.
So in this, doesn't it look like the particle actually has a T mu all the way down to the horizon? I mean, can I see it's not the case like that here?
Yeah, we actually, yeah, so actually, we had earlier papers in which we claimed there's a firewall, but then later on, we realized that actually, when you trace it backward to the horizon, the uncertainty in the frequency is so large, it's dramatically large, so that for any finite frequency range, the amplitude goes to zero. So you don't expect to actually see any particle of high energy.
You do have a non-vanishing T mu nu. That's what I mean, so this is your correction.
Yeah, that's a hand-waving argument. We should rely on the algebraic calculation. Sorry about that.
But if you're going to add this to your action, then presumably it also does contribute to an energy momentum tensor.
Yeah, we didn't consider that actually. So I mean,
Wouldn't the
I
same
think
sort of reasoning tell you that if you have large derivatives of phi,
Uh-huh.
you'll have some large energy.
Yeah, so if you consider that, then we do expect a large energy momentum tensor. That's right. So the expectation value of the energy momentum tensor flux could be large. I was saying that individual particle doesn't really contribute a high energy particle. The probability of finding high energy
I mean,
particle.
this is a correction to the state. So you say you're computing some
That's
state
right.
in that
Yeah.
slightly, what you thought was a slightly corrected Minkowski vacuum.
Right.
some enormous component of some energy.
That's right. That's right.
Okay.
But since this is only signaling the failure of EFT, so I'm not sure how much we can take the conclusion seriously. Okay, so maybe we'll take a 5-minute break and then come back for the UV models as examples. Okay, so we were saying that effective theory breaks down around scrambling time. So in principle, we cannot trust prediction of Hawking radiation within effective field theory. But on the other hand, this doesn't necessarily mean that Hawking's prediction is wrong, because we still need to consider UV theories. And often people believe that any sensible UV theory cannot produce anything dramatically different. And there are good reasons. So one important argument is to say that what we need is merely this exponential blue shift factor. Whenever we have this blue shift factor between the definition of vacuum in terms of capital U and detection of particle in terms of little u, you would have Hawking radiation. It doesn't necessarily have to involve transplanckian modes. So you could have people detecting Hawking particles here, and then you trace it backward in time. If you trace it backward in time all the way to the collapsing matter, we were saying that there would be transplanckian Lorentz invariant quantities. But you don't have to trace it back so much. You can trace it back only up to a certain point, such that R minus A is much smaller than A, so that this approximation is good. But this is not too small. We make sure that this is not too small. For example, this is still much larger than Planck length. So the momentum of this detected particle, little omega, is of order 1 over A, and you trace it backward in time. Over here, it's not defined with respect to capital U, but it's blue shifted to some large momentum, but still well below the Planckian scale. But as long as it is sufficiently close to the horizon, you would have this exponential relation, and then you can argue for Hawking radiation. So all you need to assume is a vacuum state here. So if you have, we assume initial state to be the vacuum annihilated by annihilation operator A. If it propagates here without too much change, then you would automatically reproduce Hawking radiation. So actually people have been considering many different UV models. A large class of models were focusing on the modification of dispersion relations. So usually for massless particles, you have this dispersion relation, but people consider all sorts of different dispersion relations, including those with a cutoff. So you can assume your dispersion relation at low energy goes linearly like that, but then maybe it goes to a finite cutoff instead of, or other different dispersion relations, but they all reproduce the same, essentially the same Hawking radiation. So there is indeed a robustness in Hawking radiation. Another argument is the nice slice argument, which is saying that I can define time slices, space-like time slices across the horizon, such that everywhere the extrinsic curvature is small. And then by adiabatic theorem, effective field theory should be valid for the description of time evolution along time slices, along these nice slices. Now that argument is not, in my opinion, not as strong as the previous one, because that argument is essentially only saying that for freely falling observers, they can use low energy effective theory to describe their experimental results. But if they decide to do a Transplanckian measurement, if freely falling observer decides to do a Transplanckian measurement to see if you have a particle within a Transplanckian scale box, the person would still need to use UV physics. So the point is just that for a distant observer, when they consider a wave packet over here, it corresponds to a Transplanckian particle for freely falling observers. So for them, they still need UV physics. So nice slice argument is not so strong, but the previous argument saying that all you need is a vacuum state a bit away but not too far from the horizon, that is a stronger argument. So the necessity of giving something, a different prediction of Hawking radiation is to change the vacuum state a bit far. So you need some sort of non-locality, otherwise it's very hard.
So, what does this say about Rindler horizons?
The what?
What does this argument say about Rindler horizons?
Rindler horizons, that doesn't say anything about that because there is no collapsing matter. So you still have the complete Lorentz symmetry, so you can always boost the energy of every particle. So there's no notion of Lorentz invariant Transplanckian.
What I meant was, okay, so obviously I need curvature around to activate this term in your effective.
Right, so if you have no collapsing matter.
So let's take the sun, okay, and let's consider erecting some Rindler horizon in the vicinity of the sun.
Right, so in Rindler space, R is 0, right? So this.
That's what I'm saying. So
Oh.
let's perturb.
Oh,
space.
perturb it.
Okay, let's put the sun over here. Okay, and when we put a Rindler horizon over here.
Right, right,
So not that curvature. So your term in the effective action
Right.
is operative.
right.
But near my Rindler horizon, I have these large U derivatives going on. So
That's right.
why doesn't flat space, near the sun get some weird?
Well, in principle, if you have, basically, if you have some perturbation, so basically what I'm having is just a source term here, right? And I have higher derivative contributions. And when the frequency gets Transplanckian, you have a large contribution. That's it. So, if you design such an experiment in Minkowski space, you would also say effective theory breaks down. But we are not saying that implies we see a lot of particles coming out. That's what I'm trying to deal with right now. Right. So I'm only saying effective theory breaks down whenever you have Lorentz invariant Transplanckian quantities. And I show explicitly. Well, it's not the, it's.
I don't think we would expect there to be some weirdness in the Minkowski vacuum.
If you look at Minkowski vacuum at Transplanckian scale, you could be seeing something different from effective field theory, right? Although you probably are not expecting like crazy explosion, but you would say effective theory breaks down if you are trying to probe a very short distance that's shorter than the Planck length, right? So I'm only saying effective theory breaks down when you do Transplanckian measurement.
Is there a difference between very high frequency modes, which are already present in the vacuum, as compared to high frequency modes in an excited state?
Right.
So what I meant to say, in a Hawking radiation, the conversion of those high frequency modes into some excited state.
That's right.
Some of the
Exactly.
observed.
That's right.
But I mean, normally, I mean, when you on field theory, the vacuum is full of this high frequency.
That's right.
It
Mhm.
doesn't bother us.
That's right.
So why would it bother?
So it doesn't necessarily bother us until we find explicit examples,
Ah,
right? So as I was saying, so far it doesn't really give you any concrete conclusion. We only know that Hawking's result could be wrong. There's a possibility, but it's also possible that all sensible UV theories does not give you anything different from Hawking prediction, right? So saying that sounds like I shouldn't have even talked about what I just did. But
Same question maybe in a slightly different way. You can write down an amplitude like that, but sometimes when you actually try to calculate it, there is an energy conserving delta function, right?
That's
So-
right.
and
Very
that
good.
Kills the amplitude. Like normally you can always create a pair of particles, but when you integrate over dt, if the energy is not
Right.
conserved,
So we actually explained in the paper in a section how that delta function doesn't really matter. Essentially, in Hawking radiation, the reason of Hawking radiation is that a given frequency at large distances corresponds to a wide spread of frequencies such that positive frequency at large distance involves negative energy around the horizon. So this effect weakens the delta function energy conservation. It's still a suppressing factor, so you need higher derivatives, sufficiently high derivatives to cancel that suppression. So let me go over some of the examples. So basically, all these examples show a similar feature. This is the space-time uncertainty relation proposed by Yonea-san. And if you have a massless particle of energy E, you would say that maybe it involves uncertainty in time, like this. And for massless particle, this is also the same as energy is the same as the momentum. So this expression essentially tells you that you have some relation like this. Actually, for the case of Hawking particle, as I was saying, you have when you have large momentum, it also translates into large uncertainty in momentum, because if you have a wave packet here, if it's positive frequency, when you transport it backward in time, it would have to have a very large uncertainty in order to involve some negative frequency so that you can mix particle with antiparticle, and that's how you can say there is particle in vacuum. And so this is also some sort of UV-IR relation. When you go to high energy, you also have a large infrared uncertainty. And while this is covariant, this is not. We also consider this kind of relation, which is also covariant. So we will see several examples exhibiting similar uncertainty, space-time uncertainty, although they will give different results in Hawking radiation. So we are not sure yet what is the critical physical or mathematical ingredient, but we just, given any concrete UV model, we can just do the calculation. So the first example is GUP. It's the generalized uncertainty principle. It's proposed by string theorists to say that because when you have strings carrying a large momentum, it typically has a large extension. So if you mix that extension in space together with the uncertainty in the standard uncertainty principle, sorry, this is plus, you modify it like this. And then at large delta P, you get so this is just like what I wrote earlier, right? On the other hand, this equation also implies the minimal value of delta x. So this model has already been considered by other people quite some time ago to see how Hawking radiation is modified. And we simply copy their formulation. So we didn't try to create some new models. Then people may say we are doing crazy things. So we are doing crazy things that other people have already done. So it's maybe better justified. So the standard way to realize this uncertainty principle is to impose this commutation relation. I'm sorry? Uh-huh. Right. Yeah, I mean, this is dimensionless, so this has to be dimensionless also.
Yeah, but so you cannot get delta S larger than L. So I guess that you should consider delta S squared. Right?
Anyway, I thought it's something like this. I mean, the dimension is correct, right?
That's the point. Let's say probably this kind of, but I expect the first one dimension is.
Yeah, anyway, so I'm going to use this. And then so we just, sorry, this x, when I implement this in the calculation of Hawking radiation, I have to choose a certain reference frame. So the calculation is in principle depending on the choice of coordinates, but in the end, we consider the whole class of freely falling frame. So when people consider UV theories, typically you impose your UV modification in a certain reference frame. It's not justified because the collapsing matter choose a preferred frame. But typically people want to say that for freely falling observers, at least, they shouldn't notice anything exotic. So you impose a small UV correction for the freely falling observers. But freely falling observers are not unique. So we actually considered freely falling observers starting with all possible initial velocities and let them freely fall. And we implement this commutation relation in all of these freely falling frames. And we check that the conclusion of Hawking radiation is actually the same. So here I'm only considering a special case. So here we are considering this metric. And we say that R is A plus X, and we identify this X with that X. And so, and also this A describes a thin shell. The thin shell is falling at V equal to 0. And this is the step function. And then so we can write down the wave equation, but with every X replaced by an operator on P. So in the end, we get so the wave equation for outgoing modes would look like this. So we do Fourier transform so that P is the momentum and X is realized as an operator acting on P. This is X. And so the classical case is with L equal to 0. Then you get the standard wave equation. Here I'm using coordinates V and R because the ingoing Vaidia metric is suitable for freely falling observers. This corresponds to freely falling frame with the initial velocity of speed of light. What is A?
Notation. I'm confused with this AV is equal to A H V.
Yeah.
Oh, theta. Okay.
Sorry. Sorry.
Okay. Thanks. Then I'm done. Okay. Then I'm done. So it's a
Sorry.
step function.
Thank you. Sumit knows what I'm writing. Okay, so we just solve it and then compute the same thing, the number operator, and then we get so remember earlier we considered the low energy effective theory calculation in which we get a similar expression and say that there would be a cutoff in the coordinate u when you have a cutoff in momentum. Here, this algebra gives you a minimal delta x, so it does have a cutoff in momentum. So you reproduce the same expression we had earlier. But as I was saying earlier, this is not a good sign because this is saying that you are, you are cutting off very high frequency modes. And it's saying if I have a high frequency mode propagating to low frequency mode, and now this mode doesn't exist, then I cannot excite it over here. It's a little bit strange. So this corresponds to the fact that the inner product you define for this theory would not be, strictly speaking, conserved for this process of Hawking radiation. So it's like when you you stretch the horizon and then suddenly some modes cannot be found. So in the paper where they first considered GUP on Hawking radiation, they say, oh, this probably reflects the fact that you have a string reservoir around the horizon, so that very high momentum modes should be described as strings. So it's not included in the field theory. So anyway, they didn't give this final result because they didn't try to consider time-dependent Hawking radiation. So they thought Hawking radiation would be essentially the same, although they noted this problem of conservation of inner product. Now, so this is not a good example, but what it says is that Hawking radiation stops after this time, which is half of the scrambling time. It still has the same Hawking temperature, and the radiated energy compared with the initial energy is the negligible portion. So it's like that, of this order of magnitude, a tiny portion, so you can ignore that. Okay, so GUP gives you this result. Yes?
So what do you wrote as B psi dagger B psi? that psi has a variable, which is your U naught.
The psi has a large U naught, that's right.
There is a U naught there, right?
Yeah.
So that's that U naught. Okay.
Hmm?
And so what I was going to ask you is that what is this cutoff on? This cutoff is telling you that if U naught is larger than certain value, then there's nothing.
Yeah, so you have a cutoff of momentum. You have sort of highest momentum.
Right.
When you extrapolate backward in time, Hawking wave packet, it goes beyond that cutoff momentum. Yeah. Okay.
So that's why it's beyond scrambling.
Yeah, that's right. Okay, so next example is motivated by string field theory. In string field theory, if you consider string field theory Minkowski background, typically you have the usual kinetic terms. So for a scalar field, you would have this kind of kinetic terms. But with interactions, interactions only appear in the jest operator form. You would have something like this. The coefficient is not necessarily exactly string length scale squared. But the point is that there is a exponential suppression of high frequency, high momentum modes. So in string theory, typically when you calculate scattering amplitudes, the scattering amplitude is exponentially suppressed in the Transplanckian high energy limit. So when you use string field theory to reproduce those results, you have a result like this. You have exponentially suppressed fields appearing in all the interaction terms. So we can do the same thing. We have this ingoing Vidia metric, and we identify this term and this term as the metric for Minkowski space, and we can think of this as a background. So we are not taking gravity as a, playing a very special role. This is just like in low energy factor theory, you can have analogous effects like Schwinger effect and other effects. But if that interaction is suppressed in the UV limit, like in string field theory, then we can just modify the wave equation. So then the wave equation is derived from such an action. So this is the action you get from the ingoing Vidia metric. But now, for this interaction term between the interaction between the gravitational potential and also the radiation field, I use this phi tilde, the exponentially suppressed, high energy suppressed field. And so this action gives you a wave equation, which we can solve. And then we get a result like this.
Sometimes people put that exponential factor in the kinetic term rather than in the potential term. I mean, some people you get.
Yeah, then you get exponential minus.
That's right.
That's right. That's
Minus
right.
this thing, right.
Yeah, yeah, you can do either
But
way.
something would be I mean, see, this part is part of interactions.
Right.
But if I put it in the kinetic term,
Yeah.
even the free theory will have
That's right.
an effect, right?
That's why we had two papers. I listed two
Oh,
papers. In one paper, in the first paper, we moved the higher derivative to the kinetic term, and then the correlation function is changed.
Right.
2-point correlation function.
Yes.
And then, so no, you no longer have the usual singularity. And then the calculation is different. Here I'm presenting the second paper. Yeah. Huh? Which way is better? The reason why this is the second paper is this way is maybe. In the first paper, we actually had to try to develop a Hamiltonian formulation. So we did something like we have to analytically continue the string length scale to formulate a Hamiltonian formulation, and then we can calculate that. So we're starting from the correlation function, two-point correlation function. We try to read off the time-ordered product of the field operator, but we need this analytic continuation to do that, and after that we can do the usual Hawking radiation calculation. And here we are doing it in the standard, more standard way. So somehow we didn't realize that we could do it this way. Huh? Same theory, just different ways of treating the fields. As Sumit was saying.
After you do the field definition, the measure is also changed. And you do not introduce this measure effect in the
Why don't we? I mean, we thought we did take care of, you know. That's why in the first approach we didn't use Lagrangian formulation. We used Hamiltonian formulation. That's what I was saying. We used Hamiltonian.
This measure effect we also have some gradient effect in the Hamiltonian formulation. So in this sense, I usually don't know how to do this computation.
Yeah, usually we don't know. So we have another paper explaining how to do that. Yeah. So we have a third paper which we didn't list, but it's focusing on the Hamiltonian formulation. Why that's justified. We used it to calculate Hawking radiation, and then the result is similar. So in this case, the situation is different. Here we have a cutoff not because there is a cutoff in the momentum in Hilbert space, but because this exponential suppression is saying that basically you can ignore this term when you go to very high energy. So for very high energy modes, they are just propagating in Minkowski space. So they don't contribute to Hawking radiation. So it's for a very different reason. So now I should go to the third example. The third example is non-commutative geometry. So non-commutative geometry is a simple way to realize this space-time uncertainty relation. And we can realize this by the Moyal product, or in any other way, it doesn't matter. So then we get, but the problem is that we cannot do the naive, we cannot use the naive action because that would be singular. Let me explain. So in the end, we try to modify the wave equation in this way. So phi plus refers to positive frequency modes. So if I take the complex conjugate of phi plus, I would get phi minus. And here, the non-commutative product only, the Moyal product only involves the step function for the collapsing matter and also the field. It doesn't involve this 1 over r factor, because if we put this inside, this 1 over r would be shifted and there would be a singularity and the equation would not make sense. And also we have to restrict it to positive frequency modes because the Moyal product has the effect of shifting the v coordinate by the momentum of the field after. And we have to make sure that's shifted in a way compatible with causality. So if we take the complex conjugate of this equation, and then we get the equation for phi minus, and then in the end, it's equivalent to, sorry, this P, to this equation. So here, this phi is the Fourier component of the massless field phi. And then this Moyal product has the effect of shifting this coordinate v according to the momentum. But because of the choice I mentioned earlier, this shift is always positive shift to be compatible with causality. Otherwise, you could be having a modified equation even before the collapsing matter enters. So we don't have much choice if we want a well-defined modification of the wave equation. We have to take this one. And then we just go ahead with the calculation. For a wave packet psi, the answer is, so there is a coefficient in front that I omit. We still have the same temperature as we have explained before. But in this case, it's not the cutoff, but rather a decay, a 1 over u0 decay. So it leads to a slower decay of the Hawking radiation in comparison with the previous examples. And you can ask the question, how long does it take to decay? And the answer is that it would take, the evaporation time is essentially the Poincare recurrence time. So there's a number alpha here, which is related to how many species of particles you have, which would affect the evaporation rate. And this is the Bekenstein-Hawking entropy. So this is essentially the Poincare recurrence time. So basically it's saying that before you completely evaporate the black hole through Hawking radiation, there should be some other ways of decay process that are relevant. So in practice, you can say this can be ignored after the scrambling time. So this equation is valid only after scrambling time. Okay, so we see 3 examples. They all exhibit some feature like the space-time uncertainty relation, but they have quite different implication to Hawking radiation. But basically, roughly speaking, Hawking radiation does not persist in these models, while they do persist in most of the UV models people have considered. And actually, we have also considered a lot of UV models in which Hawking radiation persists, but we just didn't publish them because there are already many, many papers. So to conclude, Hawking radiation has many reasons to be robust, as we explained earlier. But what we found is that the Hawking temperature is the part that's really robust. And with the Hawking temperature, you can always derive the Bekenstein-Hawking entropy through thermodynamic laws. And so we are not changing the Bekenstein-Hawking entropy. But the amplitude changes over time. So for the dynamical black hole, Hawking radiation is time dependent. This time dependence is not observed before because people didn't try to compute time-dependent Hawking radiation. They typically just checked the temperature. And also a key feature here is that in any of these examples, a crucial ingredient is that the geometry is depending on the momentum. When you have Hawking particle traced backward in time, it has a different momentum depending on the time. At later times, it has higher momentum. If the geometry is momentum or energy dependent, then you would change Hawking radiation. It's just like changing Schwarzschild radius if Schwarzschild radius is momentum dependent, you would say you have different Hawking radiation, right? So it's in some sense similar to asymptotically safe gravity. You have a Newton constant that runs with momentum. So geometry is momentum dependent. Here we also have a geometry that's momentum dependent, although we see quite a few different ways. So that's basically what I like to say. Are there questions?
So it's just a comment on the last thing you said. If you have a temperature, then there is a following relation. If a body can absorb, it must also radiate. That's the detailed balance condition of thermodynamics. So if you have a temperature and it is not radiating, it also means it cannot absorb.
That's assuming thermal equilibrium. But
Yes.
Here, this is a dynamical process. So it's more like you have a black body radiation with a hole coming, with a black body radiation coming out, but the size of the hole is decreasing. So there are other examples in the past where people see thermal radiation, but time dependent because it's essentially a dynamical process.
But if the size of the hole in your model was decreasing, it also means the absorptivity is going to zero because the body can't absorb because it has no.
Right. But the temperature of the gas inside can remain
Yes.
constant temperature. Yeah. So that's what I'm saying.
So this modification happens at scrambling, that's like m log n.
Yeah. A log m. That's right.
So that's way before
Page time.
MQ, which is page time.
That's right. So the energy loss can be essentially neglected. So basically, we have a classical black hole. So we are resolving the information paradox by saying there is no quantum black hole, just classical. So everything's fine. Well, I'm pointing out this alternative possibility. Yeah, so it's not easy to have UV models exhibiting, but it's interesting that they do exist. Yeah. Okay, so if there's no other question, please enjoy coffee break.